Okay, lecture 2, basics of functions and graphs. So in this lecture, we will talk about what is a function, graphs, equations, and functions, and how they're related. How do you tell if a graph is a function or if an equation is a function? Vertical line test and solving for y are the answers to those. What's functional notation and how do we use it? What's domain and range? How do you find that? How do you express it in interval notation? And then finally, an application to business, fixed and variable costs. So function has got three parts: a domain, a range, and a way to get from the domain to the range so that each thing in the domain is associated to exactly one thing. And this is an important point, exactly one thing in the range. In this class, generally our functions are tables, graphs, and equations. Those are most of the ways that we will see functions. So which of the two graphs below is a function? Well, to answer this question, you have to understand how graphs provide a rule to get from the domain to the range. So the domain is the x-axis. This is where we start. Domain. And the range is the y-axis. That's where we want to end up. And what a function does is it tells us a way to get from the domain, that's from the x-axis, to the range so that everything in the domain gets one thing in the range. So how does that work for this function? Well, if we pick an x value, that's something in my domain, I want to be able to get to the range, which is the y value. How do I go about doing that? By using this graph. Well, you go up till you hit the graph, and then you go over. And so that gives me my x value of 2.4 gets mapped to the y value of 2.4 as well. So there's my x and there's my y. If I pick a different x, say x equals this x value, that's 1,246 minus 0.6 is my x. How do I figure out my y? Well, I go down that vertical line till I hit the graph, and then I go over to the y-axis and I read off what my y value is, minus 2.246. So this x value gets this particular y value. So is this a graph of a function? Well, that's the question is, if this is the rule to go from the domain, x's, to the range, which is y, is to start on the x-axis, go up or down to hit the graph, and then go over to the y-axis, does each x get exactly one y? And the answer is from this picture, sure, right? If I pick an x value and I look up and down, there's only one place where that vertical line crosses the x-axis, the graph, and that gives me my only y value. So this is a function. Here, though, if I take, say, x equals minus 5, can I get to a y value? Sure. I go down, and I go over, and I get my y value, whatever it is. If I take x equals minus 2, though, do I get exactly one y value? And the answer is no, because there's actually three possibilities. There's one there, or you could go up to this place where it hits the graph and you get another one there, or you could go down to here and you get that one. So x equals minus 2 has got three possible y values: y equals 2, y equals 0.4, and this looks like y equals minus 2.2. Which one does it go to? Well, we don't know. So not a function. Right? So what's the rule from getting from the x-axis, which is the domain, to the y-axis? The rule is go up or down from the x-axis to the graph. So grow vertically, then horizontally, left, right, y-axis. And that will take you from an x value. You do this procedure, and then you end up with a y value. Okay, so that's how graphs give you a rule for getting from the x-axis to the y-axis. So here's two functions. Which one gives you a function? Y is a function of x. So how do equations give you a rule to go from one collection of numbers, that's your domain, in this case, represented by the x, right? Domain of the x values to another collection of numbers, right? And that's the y's. So if you're given an equation and you want to know, is this equation a function? Well, you solve for y. So y minus 3x squared plus 5 equals 0. We solve that for y. What do we get? We get y equals 3x squared minus 5. And so if you know x, right, if x is given to you, x equals 2, for example, then you know what y equals. Y is 2 squared is 4 times 3 is 12 minus 5 is 7. So if you know x, there's only one possible y. So that's a function. What about x squared plus y squared minus 9 equals 0? We try and solve that for y. What do we get? Well, we get y squared equals 9 minus x squared, right? Move the 9 and the x squared over, and then we'll take the square root of both sides. But you have to remember that every number has got 2 possible square roots. So we have to put a plus or minus in front of there. So if you know x, if x equals 0, for example, then y is plus or minus square root of 9, which is plus or minus 3. And we have 2 answers. We don't just have one, right? So this particular x actually gives you 2 y's, and so that's not a function. So a function then is a rule that takes each thing from the domain and assigns it exactly one thing in the range. And a variable is a letter that stands in for the things in the domain or the things in the range. Usually we use x for domain and y for range. So if a graph passes the vertical line test, it's a graph of a function. If it can be solved from variable without any choices, then it is a function. That's what the 2 examples we just saw were. So I'm going to go over to GeoGebra for a moment. Where's my GeoGebra screen? I don't actually have it up. I should have it up. Ah, there it is. Okay. There's my GeoGebra screen. So those last example, one was y equals 3x squared minus 5. We can type that into GeoGebra, and we get that, right? And we're claiming that no matter what x you pick, you get exactly one y as your output. So if x equals minus 1.5, right? If I start at x equals 1.5, I go up to the graph. It only hits the graph, this vertical line only hits the graph one place, right? And that intersection is my x coordinate and my y coordinate, right? And if I pick a different x value, say 1, right, I get a different vertical line, and that vertical line also goes through the green line in exactly one place, right? If x is 1, then y is minus 2. Okay, good enough. So we can delete that and delete that, and we'll graph x squared. This is one of the nice things about GeoGebra is that it can graph equations where you have the x's and y's and you don't solve for anything. So here's x squared plus y squared equals 9, which was the second example. It's a circle, radius 3, centered at the origin. And again, if I take x equal to 1, right, x equal to 1, well, I can go up to the graph, and that gives me 1 point, and the y value is this nasty thing. Or I could go down, and that gives me a different y value. So I get 2 y values. One's the plus, one's the minus. And so that gives me my shows me that this isn't a function, right? Because it doesn't, because you get two y values for each x value. Okay, so again, GeoGebra is useful because you can also enter in functions, equations like that. This isn't a function because we plug in, say, x equals, it has to be small, so x equals 0.2. Right? You can see that that line goes through this gray curve in 3 places. And so the gray curve is not the graph of a function. But GeoGebra allows you to graph, you know, any kind of equation that involves x and y, which turns out to be really useful in a lot of different contexts. And it's one of the reasons why I use it a lot. So to go back to the notes, there it is. So vertical line test, if it passes a vertical line test, if you draw the graph and every vertical line goes through the graph exactly once, it's a graph of a function. If you can solve an equation for a variable, like y equals something involving x, and you don't have any choices, like the plus or minus, then it's also a function. So generally we use x and y as variables. So for like in this example, the x's can be replaced by any number you want, right? You can place x by 2 or 7 or 15. And then the result of the calculations is corresponding y value. If we want to emphasize the fact that this is a function of x, we use this notation, f of x. The f is just a name. It's not anything really. It just stands for function. And we use different names for different functions as we go through. And this kind of notation turns out to be really useful because it allows us to calculate things pretty quickly. So if this is our function, what's f of 2? Right? And so what did we do here? When we look at f of 2, that means I took the x here and what I did is I just replaced this x here by this 2. So f of 2 is going to be, well, that means I replace all the x's here also by 2. So it'll be 2 plus 2 quantity squared times 2 minus 1. And if we follow PEMDAS, right, we have to 2 plus 2 is 4 times 2 times 1, because we do everything in the parentheses first. And then that's equal to 16 times 2 is 32. That means if I graph this, that would mean that the point 2 comma 32 is on the graph. The tablet is acting up a little bit weird today. Okay, what's f of minus 2? Same deal. Wherever we have a x in the formula, you replace it by the number minus 2. So it becomes minus 2 plus 2 quantity squared times minus 2 times minus 2 minus 1. And that would become 0 because minus 2 plus 2 is 0 times minus 2 times minus 3, and that's 0. What does that mean? That means minus 2 comma 0 is on the graph. What it also means is that the y value is 0. So x equals minus 2 is an x-intercept. Right? Whenever you get a y value of 0, that means you're dealing with an x-intercept. F of h, what is that? Well, that just means that I'm replacing the x with an h, which doesn't really do much of anything. It just changes the lettering around a little bit. I'm not going to multiply that out because that'd just be tedious. What about f of x minus 2? What that means is I'm taking this x and I'm replacing all the x's by the quantity x minus 2. And we're replacing things with kind of complex expressions like things with subtractions in them, I'm going to put it all inside of a parentheses so I don't screw up the order of operations. X minus 2 minus 1. So x minus 2 plus 2, that's just going to be an x. X minus 2 is just x minus 2. X minus 2 minus 1, that's x minus 3. And I'm not going to multiply that out, but you could if you wanted to. So if we have a formula like this, the thing inside the parentheses, right? You just take that and you plug it in wherever the x is in the formula, and that gives you the replacement. Okay, so for any function y equals f of x, we've talked a little bit about domain and ranges. We want to know two things. What are the things that we can put in for x? What are the numbers that can be put in for x? That's the domain. And what are the things that we get out for y? This is the range. Generally for graphs, domain is horizontal, that's left, right. Range is vertical, right and left. So here are two functions, an orange one and a blue one. We want to give them names and find out the domains and ranges. So first off, we have to label our x-axis. This is our x-axis. These are days. So I'll call this D for days. And then my y-axis is here. And I'll call my y-axis T for temperature, and it's measured in Fahrenheit, degrees Fahrenheit. So there's two functions. One is the orange one and one is the blue one. So the orange one is T equals, well, those are high temperatures, so we'll just call it high T. So there's a function, that's the orange function. D is the variable, it's days, day 0, day 1, day 2, day 3, day 4, day 5, day 6, day 7, blah, blah, blah. T is the output variable, that's the temperature, 60 degrees, 50 degrees, 40 degrees, 30 degrees, 20 degrees, 10 degrees. And high is the name of the function. It's the orange function. We're just calling that the high function. So the domain are what things on the x-axis that you can plug in, the horizontal axis that you can plug in. Here it's actually a d-axis. And we start at -1 and we go to 28. So the domain is -1 is less than or equal to d is less than or equal to 28. Take any day, any time between -1 and 28. And know that this is actually the 0th day of February, for example, that would be January 31st. We have something called interval notation for spreads of days written like this. We would write it like that. The square bracket means that we're including the endpoint -1 that corresponds to the less than or equal. The range is how far the graph goes up and down. So the orange graph, the top of the orange graph is here. That looks like, we'll call it 48 degrees. The temperature never went above 48 degrees. T for temperature. And then what was the coldest the high got was either here or here. Those both look the same, say at -2. So the high temperatures were from -2, that's the bottom of the orange graph, up to 48, that's the top of the orange graph. So in interval notation, we'd write it like that, include the -2 and the 48 by writing the blocks. I generally prefer the inequalities because it tells me that D is the domain and capital T is the range. We have another function that connects the same two variables. The low temperature function, that's the graph in blue. But it's still connecting days to temperature. So we use the same variables, but it's a different function, so it's got a different name. So the domain is the same. We're allowed to use any days between -1 less than or equal to D less than or equal to 28 or -1, 28. The range though is different because what we're looking for now is what's the lowest low temperature and the highest low temperature. Lowest low temperature is here. This is the bottom of the blue graph. That's like -18. And what's the top of the blue graph? That looks like it's here, right? So just above 30, we'll say, call that 31. So those are my range of my low temperatures, right? The low temperatures range from -18 to 31. The high temperatures range from -2 to 48. The domain is over what stretch of days? And the stretch of days is from January 30th to February 28th, or D equals -1 to D equals 28. So domain is left and right, range is up and down. So to find the domain of a function from a graph, find the limits of the graph to the left and right. To find the range, find the limits of the graph up and down. So we use inequalities in interval notation previously. We'll do the same thing here. Here's another graph without any interpretation, right? So there's no days and temperature and anything, just x's and y's. Why is this a graph of the function? Well, it passes the vertical line test. Any vertical line that goes through this, any vertical line hits the graph and at most 1 point. So how is it a graph of a function? Passes vertical line test. What's the domain and the range? Domain is left to right. So the function starts at -6 and it goes all the way to 9. So domain is left and right. And that's -6, but there's an empty hole in the graph here. So -6 actually isn't the domain. There's no y value here because it's an empty hole. So it's a strictly less than. And then x is less than or equal to 9 because this one is filled in. And we write that like this. The square bracket means you're including the endpoint. The parenthesis means that you're not. The range is from the bottom to the top. So the bottom of the graph is at y equals -3. That's here. And the top of the graph is up here. So we don't include that point. So the range is -3 less than equal to y less than 3, because we don't include that 3, but 2.99 something, something, something. And notice when we're writing the inequalities, you always go from lower to higher, -3, y3. And in interval notation, it's this. The graph does get all the way down to -3 because this is filled in. Doesn't quite get all the way to +3 because that's not filled in. Great. X-intercepts. If this is the function y equals g of x, what are the x-intercepts? The x-intercepts are where you go through the x-axis. There's one here, there's one there, and there's one there. So 3 x-intercepts. And usually for x-intercepts, I just write them as x equals, I think that's 4.2 -1, 6, just sort of list them. We know the y-coordinate is going to be 0. What's the y-intercept? Well, the y-intercept is where you go through the y-axis. That's here. That's x equals 0, y equals 1. So my y-intercept is just y equals 1 because we know that at a y-intercept, the x-coordinate is equal to 0. Okay. Find g of -3 and g of 5. So what does that mean? G of -3 equals what? Well, this expression is telling me that x equals -3, and I want to know what is the y value. And we know how to read a graph now, right? If we go to x equals -3, so there's x equals -3. We can go down to the graph until we, up or down to the graph until we hit the graph. And then we go over to the y-axis to read off the number. So g of -3 equals -2 because that's what the y value is. So that's here. Great. G of 5, right? What's G of 5? Well, that means we go to x equals 5. That's here. And then we go up to this point on the graph and we read off what its y value is. Its y value is 1. So G of 5 equals 1. So that's an x value. We want to know the y value. This is an x value. We want to know what the y value is, and that will turn out to be -2. So find all x's that satisfy g of x equals 1. So if we take g of x equals 1, this is a y value. They're asking what is x? So if we take y equals 1, that's here, what are the possible x's? Well, that means you go horizontally. We have an x value here, 5, and 0 also. If you start there, you'll end up at a height of 1, and then the other one, the height of 1 would be way out here. So to get a y of 1, you could either start at -4.8 and go up and over, and that would give you 1, or you could start at 0 and that would give you 1, or you could start at 5 and that would give you a y of 1. So we actually have 3 possibilities. Right? So each x gets exactly 1 y. Each y could have many x's. And then the last question is, what are all the x's that satisfy g of x equals 2? So again, this is saying if y equals 2, what could x be? And when we go back up to the graph, we say, okay, y equals 2 is here. Y equals 2. What are possible x's? Well, there's one way out here. And this is -5.4, I guess. And then there's a whole bunch, right? All the numbers from 1 to 4, and these are filled in dots. That includes all of them. So what are x's that satisfy g of x equals 2? What are x's that when you put them into this function, you get 2 out for your y? Well, -5.4 and any number between 1 and 4, right? Any of the numbers in here. So any number from 1 to 4, including the endpoints. So how do we write that in interval notation? Well, a number all by itself is in curly braces like that. 1 to 4, we know what that is. We want to include the endpoint, so it's 1 to 4. If we have 2 separate things that we want to join together, either this or that, we use a U. That's the symbol for or. So in interval notation, this is the answer to this question. Good. Okay. So domain is left to right, range is up and down. If you know an x, you can find a y by starting an x value and going up to the y-axis. If you know the y value and you want to know the x's, go left and right till you hit the graph and then go down. That'll tell you the x-axis. So there's the procedure for that. If you know the x value, how do you find the y value? If you know the y value, you can find the x values, and there might be more than one x value by going left, right to the graph and going up, down to the x-axis. And here's a little thing about interval notation. So brackets means include the endpoint, parentheses means do not include the endpoint. So this is the same as this. Infinity always gives you parentheses. It just means all the numbers bigger than or greater than 154. A single point, you can either write x equals 5, or you can just write braces 5. Union symbols, right? That's what this is. Different intervals can be joined with that. And when we're looking at graphs, a point that's not included is an open circle. A point that is included is a filled in circle. And you have to be a little bit careful. This is the big Warning, sometimes this symbol means a point with x coordinate 2 and y coordinate 3. Sometimes it means the interval 2 less than x less than 3. So you have to pay attention to tell the difference. So, and the last thing for this lecture is a word problem involving fixed and variable costs. So we'll define these things. This is a business application. A fixed cost, it doesn't depend on how many things you make. So fixed costs, right? If you own a factory or store or something, rent, right? However much, doesn't matter if you make anything, you still got to pay your rent, taxes, utilities, Wi-Fi, all that kind of stuff, right? Anything that you have to pay, regardless of whether or not you make anything, maintenance. Variable costs, it depends on what you're making, right? But often variable costs are stuff that you have to buy to make stuff, right? So if you're in construction and you're building a little house, right? Wood is a variable cost. If you're building a little house, you don't need to use too much wood. If you're building a big house, you need a lot of wood, so your costs will vary depending on how much wood you use. So Bob's Donut Store has fixed costs, right? Rent, electricity, wages, etc., of $3,000 per month. The variable costs, right? And if you're making donuts, it means you need flour, sugar, delicious chocolate icing, and other stuff, 60 cents per donut. And the store has a maximum production capability of 4,500 donuts per month. What is the cost function? And sketch it. And what does cost of 100 represent? What is the domain? What's the range? Okay, so the cost function, we don't have any variables, so we have to name these things, right? And everything depends on how many donuts you make. So we'll just start by saying X equals number of donuts made, and then cost of X is the function we're looking for, cost of making X donuts. So this is a function, right? We're naming it cost, and the variable is X. So whatever function we get, it should tell me that if I make this many donuts, this is how much it costs. So cost 100, whatever that is, that's the cost of making 100 donuts. And we can actually calculate that pretty easily. You got to pay $3,000 just for having your donut store be open. And then you're paying 60 cents, right, which is $0.6 for each donut, and you're making 100 donuts. So you're spending variable costs, that's $60 on donuts, 60 cents for each donut, and you're making 100. So the cost of making 100 donuts is $3,060. So what is the actual cost function going to be? Well, we can see how that works, right? 3,000 regardless of how many donuts you make, plus 60 cents times the number of donuts that you actually make. And that's what the variable X stands for. So there's our cost function. We can sketch a graph of it. It's a line. Y-intercept is 3,000. X-intercept is, slope is 0.6. So it's going to start at 3,000. Often when you are asked to graph functions, you don't need to be too precise about it. Just need to sketch it a little bit. What's the domain of this function? Well, they actually tell us that. You can make up to 4,500 donuts per month, right? That's the maximum production capacity. So they can make anywhere from 0 to 4,500 donuts a month. This is my x-axis, donuts made. This is my c-axis, that's cost in dollars, right? So the domain is easy. They can make anywhere from 0 to 4,500 donuts. The range is a little bit trickier. We have to know how much does it cost to make 4,500 donuts. So cost of 4,500 is, according to our formula, 3,000 plus 0.6 times 4,500, which, if we grind that out, should be 5,700. And so that's our maximum cost. So what's our range? Well, we can spend anywhere from $3,000 to $5,700. Depending on how many donuts we make. You know, and we could get a little bit picky about exactly what the domain is, because, you know, they can't make 3/5 of a donut. But often in applications like this, we will not restrict ourselves to just integer values, because it makes the math a little bit easier. So domain is this way. Range is vertical. Oh, range. Okay. And that's fixed costs and variable costs. And we will run into Bob's store again.